Hello, everybody. So nice to see everybody back here. Tian Zhang is online and is going to welcome everybody back.
Okay, so I'm actually at Columbia. I'm not traveling, but I just finishing a meeting on main campus. I wish I can fly, but I couldn't. So I want to welcome everyone back to a new academic year, and today is our very first lecture in climate data science of the year. A few announcements. First, that this year we will have more frequent lectures. Alternating approximately, not mathematically, between internal and external speakers, so that we will hear both about the most exciting research in climate data science, but also hear about project updates of the center. And there will be food after each lecture. A light lunch will be served, but you should bring your own beverage, bring your own water or soft drink. Or get water from the kitchen. Also, if you are new to this lecture series and don't know where to find the latest announcement, the listing of the lectures, you should check our website. And also, there is a LEAP community calendar. If you need assistance finding those information, please reach out to, speak to any of the team members in the room or email leap@columbia.edu for more information. I think that's all.
Thanks, Tian. This is Greg. Thank you. Hi, everyone. So this semester, we also have a course that is synced with the topics being discussed in the weekly lectures. The title of the course is Readings in Climate Data Science. And if you've enrolled in that, if you could just raise your hand, we can just get so we have a handful between 5 and 10 that will be that have enrolled in that and will be regularly attending. So really excited about that. The readings that we'll be doing will be in alignment weekly with the broad topic being discussed by the invited speaker. So, and then we're going to meet all the students, just meet me for this first time in the back of the room upon completion of Julia's talk, and then I'll take you to our next room. And from then on, you can escort yourselves. It won't be any issue. So with that, I'd like to welcome our first speaker of the semester, Julia Simpson. Julia received her Bachelor of Science degree in Chemical Engineering from Washington University in St. Louis. And then you worked, I believe, as an engineering consultant shortly after that, and then came to Columbia to start a PhD in 2022. She took the Readings in Climate Data Science course that year as well. That was our inaugural year. She's here at LEAP working with Pierre Gentin, and she is co-advised also by Laura Zana at NYU. And her title today, so she has been working on improving parameterizations of heat and momentum air-sea fluxes using machine learning and maybe some models, but she'll explain nicely to us, I'm sure, here in a moment. So with that, I'd like to welcome Julia.
Yeah, so as Greg said, my name is Julia. I'm co-advised by both Pierre and Laure. I'm a PhD student at Columbia University, and today I'll be talking about parameterizations of heat and momentum air-sea fluxes. So just to kind of give an overview of where we're going today, I'm going to start with some motivation. So why are we even talking about this? Why do we care about air-sea fluxes? I'll move into kind of just outlining existing methods and their limitations, just to motivate my proposal. So what I'm going to be trying to do to improve those methods, getting into my approach, so my workflow and some anticipated questions that I hope to get at in preliminary results before moving into a summary, next steps, and wrapping up with how all this ties into LEAP. So first off, what are air-sea fluxes? So I'm going to just talk about 3 key ones that I'll be highlighting today: momentum flux, sensible heat flux, and latent heat flux. And so just real quick before even I define each of those fluxes, what is a flux? It's an exchange of a property. So and all fluxes have drivers. So this is exchanges between the atmosphere and the ocean, and each one is going to be driven by something different. So in the case of momentum flux, it's driven by wind speed. Momentum flux is actually wind stress. So if we recall from our high school physics days, stress tensors actually act in a direction perpendicular to themselves. So even though wind stress is going over the ocean surface, it's actually transporting momentum in and out of the ocean. And then there's sensible heat flux. So that's driven by the temperature difference between the ocean and the air. Heat flows from warmer to cooler. So if the ocean is warmer than the air, heat is going to flow out of the ocean and into the atmosphere. And lastly, we have latent heat flux, which is driven by specific humidity differences. If we recall from our high school chemistry days, phase changes are always accompanied by a heat transfer. So in the case of evaporation, heat is absorbed. In the case of condensation, heat is released. So as you can imagine, latent heat flux is highly tied to the water cycle. And one last thing just to call out here is that the sign convention on momentum flux is different from that on heat fluxes. So for heat fluxes, they're positive when heat is leaving the ocean. And for momentum flux, it's positive when momentum is going into the ocean, just if that comes up in any figures later today, so you know how to interpret them. Okay. This is just to give a picture of what these fluxes look like over the global oceans. These quantities are not uniform. As you can see, we've got regional and spatial patterns. So this is the mean climatology of the momentum flux on the left, and then heat fluxes, both the latent and the sensible summed on the right. And I just also want to call out that the heat flux shown on the right is almost always negative. So that means that the ocean is warming. It's taking up that heat from the atmosphere. Okay, so to put these sea fluxes in context of the climate system. So on the left, we've got a figure that shows ocean carbon, energy cycle, water cycle, and our human system. And I've just kind of pointed out right where air sea fluxes fit into this picture. As you can see, as I just mentioned, the ocean is taking up heat from the atmosphere, and specifically 90% of excess heat due to anthropogenic emissions has been absorbed by the ocean. So this is not a negligible effect. This is really important to capture. And latent heat flux accounts for about 87% of total evapotranspiration. So that's both evaporation and transpiration processes that are moving water from the Earth's surface into the atmosphere. So even though it's just a tiny piece of this puzzle, it's pretty impactful for the climate system. It's got implications for all of these things that I've listed on the side, and therefore it is very impactful for the predictability of Earth system models. And just a little shout out to a LEAP preprint paper that I'm citing there. Okay, so how do we measure these fluxes? We measure them with what is called covariance measurements. As you can see, this is just a sample of what these measurements might look like. This is a compilation of a bunch of different cruises. So even though this is maybe like 10 or 11 cruises, we still have pretty sparse measurements. We're nowhere near covering the entire global ocean. And these equations, we're measuring the wind speed is the W, and X is like that driving property. So for momentum flux, that's going to be wind speed in another direction. For sensible heat flux, that's going to be the temperature difference. And for latent heat flux, that's going to be the specific humidity. Measuring all of this over the ocean, as I just showed, is not feasible. So we parameterize it so that we can approximate it in terms of globally available predictors. So this is just kind of giving the general form of that bulk parameterization. So we've got the flux equal to the density times a transfer coefficient, times, again, that wind and driving force. And then below, I've got the three equations for momentum, sensible, and latent heat fluxes. So as you can just see that wind speed driver, which affects all of them, and then the temperature, specific humidity on the heat fluxes. And so just note that even though these bulk parameterizations enable the calculation of fluxes globally, that's why we've developed them, they are still based on sparse observations because they're developed from an empirical fit. So they are going to be limited based on that sparsity of observations, even though, again, they're allowing the calculation of fluxes more broadly. So this is how those bulk parameterizations work. These would be our globally available predictors on the left. These are the bulk algorithms that are calculating intermediate quantities, and then those transfer coefficients, importantly. And then they use the coefficients and the drivers to calculate the fluxes. And so that's how we end up with our estimates. And this process is pretty computationally expensive. It takes a while to run. Just anecdotally, like running it on my laptop, I notice, I can walk away and let it run as I cycle it through my data set. These bulk parameterizations also have other limitations, though, even amongst themselves. So these are 5 different bulk parameterizations. And as you can see, they're plotted on the right for momentum, sensible, and latent heat fluxes. There's quite a bit of spread So the x-axis should be the covariance measurement. The y-axis is going to be that bulk prediction for the 5 different algorithms. And especially at extremes and near zero, we get differences in performance. And yeah, again, so that's just based on those sparse measurements. We would love to say that this difference is just based on like the number of observations that are going into the bulk algorithms. However, we can't. That spread is not easily attributable. So these figures just show a couple samples of some smaller simplifying approximations that are included in these bulk algorithms that can have pretty wide-reaching effects. So on the left is showing the difference if approximation of a fixed air density is used, as opposed to updating everywhere globally. And then on the right is showing an approximation of the relative error. So this ties into latent heat flux. So the specific humidity of seawater requires an adjustment for the salinity just to account for the salt in it. If that adjustment, it's just 2%, isn't made, you start to see differences. And again, it increases at higher wind speed. So these differences are made in some bulk algorithms, not made in others. So we can't even make like a one-to-one comparison there. This spread matters, it's impactful. So on the left, we are looking at the difference between a couple of different bulk algorithms in terms of estimates of total precipitation. And on the right, we're looking at the difference of heat flux into a region near the Gulf Stream. So these differences in bulk parameterizations are measurable and impact climate processes that we care about in our models. So just to pause here, hopefully I've established that air-sea fluxes are important for climate. Observations are sparse, and bulk parameterizations have too much spread to really get at questions that are impactful for climate. So we're starting to look at machine learning now as a solution. This first paper targeted all 3 fluxes. So that's momentum on the top left, sensible heat on the top right, and then latent heat on the bottom. Each flux is targeted separately, and they actually used multiple neural networks to get at each flux. So you can kind of see where this transition is happening, especially near zero here and near zero and at extremes for latent heat flux. This was done because it was faster than bulk algorithms. So the neural network, once trained, is just computationally cheaper than a bulk algorithm. This paper, a little bit more recent, targeted only latent heat flux. And it was trained on reanalysis data. So it actually wasn't trained on bulk approximations, and it was validated with observations. Latent heat flux is particularly difficult to capture. So this was interesting to see. And they actually experimented with a couple of different machine learning techniques. So I'm just showing the result for the neural network on the right, but that was the highest performing one. And they actually only did use one neural network to capture latent heat flux. So that's just in contrast to that previous one, which again required 3 neural networks just to capture one variable. Okay, and then a more recent product targeting heat fluxes only, again, targeted those fluxes separately, and again, needed multiple neural networks per flux targeted. So in this case, they used 2 neural networks per flux. I just want to call out that the time and the temporal and spatial resolution on this is really fantastic. So this is now a flux product that goes back to 88, and it's at a 3-hourly time interval. So this is pretty good. However, it is limited by that fact that it was trained on bulk fluxes. So it's hampered by the sparsity of observations that were used for that empirical fit. So to put these current machine learning flux products in context, this is what's called a Taylor diagram. So we've got correlation coefficients going this way. We want to be close to a correlation coefficient of 1. And then on this side, we've got root mean squared error, and we want to be low on the root mean squared error. And so our machine learning product is shown here in yellow. It's right in the thick of it, performing pretty well. So this is promising. It says that these methods will probably be explored more in this field. The machine learning product here actually had the highest agreement with the buoy observations. It had a root mean squared error of less than 20 watts per meter squared and an R of over 0.83. So this was definitely better. Yes.
Good question. The bulk values are what you would want to actually model in a climate model. The
fluxes themselves are what we want to model. The bulk values I'm not sure I understand the question.
So you have buoy measurements that are
Yes.
sort of at a single point in space.
Yes.
With some temporal resolution,
Yes.
but in a climate model, you'll have spatially and temporally varying, or you'll have different time steps that you're sort of.
Right. Right. So we do want the spread, like the global representation of a bulk parameterization. You're correct in that, but the formula is just a bit too simplified. And so just going back to, again, that difference on the covariance measurements, we can't get those values globally. So it's just not, the global parameterization isn't precise enough, but you are correct that we do want that coverage. So my proposal is to actually, that segues excellently, to leverage transfer learning to get both bulk parameterizations and observations incorporated into one product. So far we've talked about the fact that observation sparsity is an issue, flux products differ, and machine learning solutions are at an early but exciting stage. And some quick work on my part confirmed that neural networks can recreate predictions of bulk approximations of air-sea fluxes. So this figure on the bottom right just shows the predicted value of the neural network that's recreating the bulk approximation against the target bulk approximation. And as you can see, we're right along that one-to-one line, which is exactly what we want for all 5 bulk algorithms that I did this for. So that's great. It just means that machine learning can quickly get at the level of these bulk approximations. So my idea was to pre-train on a global data set and existing bulk parameterizations, because again, we don't have covariance measurements globally, so we can't really train on observations globally, but then use transfer learning with observations to get at that more precise measurement. And hopefully this would give us a product with less discrepancy. Okay, so this was my workflow. On the left, we started with the pre-training neural network. So this was trained on one of 5 bulk algorithms or covariance measurements. So at this point, I've got 6 different neural networks. And then I move into transfer learning. So I do 2 versions. I do one version with a fine-tuning neural network, and that is always transfer learned on observations. So even if I pre-trained my neural net on a bulk algorithm, one of those 5, I'm now fine-tuning it on the observations. The pre-training neural network that was pre-trained on observations also just gets transfer learning on the measurements. And then below, I've got my comparison neural network. So this is to kind of represent what would happen if we were doing that same computation. We're giving something the same amount of runs through a neural network, but we never introduce observations into the picture. So for this first CoAir 3.0 bulk algorithm, it's going to have transfer learning on the same bulk algorithm down here. So note that when I get down to my covariance measurements, down here, when I'm doing my comparison neural network and it's trained again on my covariance measurements, that's going through the same workflow as my fine-tuning neural network. Does that make sense? So for all the bulk algorithms, we're pre-training on the bulk and then transfer learning on the observations. And then for the observations, we're doing that same thing again. And so I'm doing this for both separate targets. So as I established, all of those flux products target these quantities separately. So latent heat flux, sensible heat flux, momentum flux, each get their own neural network. I'm doing that as well. I'm also trying versions where I target those coefficients, if you recall, from the bulk formula, just to see if maybe we target the coefficient instead of the flux, maybe we might get some better generalization. And so for context, existing machine learning parameterizations have only looked at targeting fluxes, and they've only looked at targeting them separately. So looking at coefficients is the first new thing that I'm introducing aside from transfer learning. And then I'm also looking at grouping the targets. These values are interrelated, and at least right now, I'm feeding the same predictors into all 4. I'm feeding temperature difference, specific humidity difference, wind speed, and latent heat of evaporation to all of them. So because all of those are getting the same predictors, I wanted to see, okay, now if I am training this neural network on all 3 targets at the same time, can I get equivalent performance, or is it maybe going to degrade? And again, I'm doing that for fluxes and coefficients. And the disclaimer here is just that, as I mentioned, eventually I would love to pre-train on a global data set. For now, I'm just trying this out on that data of from cruises that I showed earlier. So we're still working with sparse observations, but we're testing out whether this transfer learning on observations can maybe improve our estimate a little bit. So the first thing I want to confirm is just that my fine-tuned neural network is better than my comparison. So I want to confirm that transfer learning on observations does in fact help, because if not, then maybe we need to reevaluate some things. I also want to compare from my separate targets versus my group targets. I want to look at, okay, if I'm targeting momentum flux, using a neural network that was trained on targeting momentum flux versus a neural network that was trained on targeting all fluxes, is it predicting that momentum flux more poorly now? Am I seeing a degradation in performance, or is it still reaching that same level that I would get if I was targeting each one individually? And then I want to compare flux predictions from models that were trained on predicting all fluxes versus all coefficients, and coefficient predictions from models that were trained on predicting all coefficients versus all fluxes. So even if a machine learning model was trained to target the coefficient, I want to make sure that when I then back out and calculate that flux, I'm getting a realistic value. And so just to give an overview of my preliminary results, my spatial and physical structures look consistent, but my mean squared error indicates some problems, in particular with latent heat flux. My fine-tuned neural network is performing better than my comparison neural networks in all cases. And my runs targeting all fluxes seem to be outperforming my runs targeting all coefficients. And targeting all targets actually appears, so that would be like all fluxes or all coefficients versus targeting them separately. They actually seem to perform the same. So that's great. That means instead of using 3 or in some cases 6 or however many neural nets to get at these fluxes, I could just use 1. So this is looking good. This is just to show that my spatial structure is generally consistent. So this is showing on the left my covariance latent heat flux. So that's the measurement. And then on the right is showing my fine-tuned latent heat flux. So that's the latent heat flux with the transfer learning on observations. And you can kind of just see, yep, we're getting those lower values in the Southern Ocean. We're getting those higher spikes in the Northern Atlantic. So this is looking reasonably okay. And actually, this was done on the run. This is coming from the models that were trained on coefficients. So even when I back out to those fluxes, those spatial structures are still looking reasonable. I also see the convergence in the behavior that I would expect in the relationship between these variables. So CD, if you recall, is the transfer coefficient from momentum flux, and momentum flux is driven by wind speed. So we see a relationship between CD and wind speed. We expect to see a relationship like the one on the left. This is just showing that for different bulk algorithms, this relationship works differently. The algorithms assume a different slope in the transfer coefficient as wind speed increases. And so when I'm training my machine learning models on those bulk algorithms, I expect to see different slopes as well, right? Because they're just mimicking that. But then when I transfer on observations, I would expect to see this convergence around the actual behavior that's exhibited by those observations. And that is in fact what I see. So again, this is promising. It's exhibiting the behavior that I would expect. Okay. And so now I'm going to start looking at my mean squared errors. So on the left is always going to be my test mean squared error, so only from the test data set. And on the bottom is going to be my targets. In this case, I'm just looking at latent heat flux. As you can see, the order of this is in the 700s. That is not where we would like it to be. And the spread from the algorithms is kind of insignificant relative to that high mean squared error. So this is the worst of it. And it is consistent on the models trained on all fluxes, trained on all coefficients, on neural networks that are even specifically targeting latent heat flux. This persists. So now if I look at mean squared error for momentum flux, I see a much more promising situation. We are much lower. So on the models targeting all fluxes on the left, models targeting all coefficients on the right, and then those blue diamonds are going to be my fine-tuned neural network. So that's the neural network with transfer learning. The green circle is my comparison neural network. So that model also had transfer learning, but only on bulk algorithms. So it's never seen observations before. And as you can see, the mean squared error for my fine-tuned neural network is consistently lower than my mean squared error for my comparison neural network. So this is promising. And as I mentioned before, the covariance one is the exception here, right? Because it underwent the same workflow both times. It was transfer learned on observations both times. And so I would expect the performance on that one to be relatively the same. And I see that. So this is promising again. And then also just notice in terms of like the scale of these bars, the fluxes, the models targeting all fluxes seem to be doing a bit better than models targeting all coefficients. But in case that wasn't a fair comparison, because I'm looking at mean squared error of a flux and I'm comparing these two things, let's look at mean squared error for a coefficient. I do see the same dynamic. The models that were trained on all fluxes are still outperforming the models trained on all coefficients. So as I mentioned, targeting all of the fluxes or all of the coefficients at once seems to perform comparably with targeting them all separately. So on the top is the runs where each flux or coefficient was targeted separately, and on the bottom is where each of them were all targeted by one model. This is just looking at sensible heat flux. And if we look at the order of these, each flux targeted is on the order of mid-30s. All fluxes is on the order of high 20s. So targeting them all together actually, if anything, appears to slightly outperform targeting them separately. And that kind of makes sense, right? Like they're all interrelated. There might be some benefit to treating them all with one model. This is looking at, so the previous slide just showed sensible heat flux. This is showing my coefficients, same thing. This is just to get at, I'm seeing the same behavior where, yeah, CH, which is the transfer coefficient for sensible heat flux, is the most difficult to capture across the board. And then we see the same behavior. Even if I'm training models specifically on that coefficient, I'm not getting a significantly better performance when I target it in with everything else. And so now to just put my work back in the context of previous work, from that paper that I showed, the first machine learning solution from 2007, 90% of the fluxes in their validation data set fell in these ranges shown on the left. And so I wanted to know, and that could limit it, right? Because we want to represent fluxes at the extremes as well. So if 90% of your fluxes are falling within one range, you're kind of worried about that. So I looked at this. This is showing the distributions of the flux estimates for all of those bulk algorithms as well as the measurements. And looking at this, my values are right in those same ranges as well. So that is also going to be a problem that I want to deal with. And so that leads me back to my global pre-training. I really want to get at representing more values. I did some preliminary work with a synthetic data set that was okay, but as soon as you start really expanding the limits on those values, the bulk algorithms actually don't really want to run because you're getting at what might be physically unrealistic. So my alternative is a satellite data set because I think that I'll just struggle less with getting a physically realistic physical system to feed into those bulk algorithms for the pre-training. I also want to reevaluate the spatial structure. So those maps that I showed were global. I think it'd be interesting to kind of zoom in regionally and see if those patterns are still consistent and just narrow the color bars because if we are driven by extremes or, there's like more minute behavior right in the middle of the distribution on the fluxes, I'd like to get a look at that. For latent heat flux, again, the problem child. Best practices, I'm going to reread that Chen paper and follow their lead. So instead of just looking at mean squared error, they actually used a few different metrics. They used R squared, root mean squared error. And I think that those could be informative to figure out what's going on. Their neural network was also very different than mine. It was much more neurons, but fewer layers. So I want to experiment with that. And in terms of targeting all coefficients and fluxes, I want to experiment with different loss metrics. So as I showed, the performance targeting all of the coefficients and fluxes together is basically the same as targeting them separately. But I'm curious if I penalize those quantities that are a little bit more difficult to learn more, if I might see a different performance. So I'm going to be experimenting with that. And then lastly, on targeting coefficients, I think that part of the reason why Fluxes is currently outperforming coefficients is those input features. So coefficients can depend on values that I'm currently not feeding in. So they're dependent on wind speed. They can also be dependent on the surface roughness of the ocean, sea level pressure, which right now I'm assuming is a fixed value. So feeding in those input features might help the performance of the Fluxes, and then I might end up with a product that generalizes better. My only concern here is, again, I want to get back to that global pre-training. So if I'm introducing too many input features that aren't available more widely, this isn't going to scale. So next time, hopefully that disclaimer is gone. I'm working with global data. And finally, I just want to give a shout out to LEAP. I've been in this organization for a couple of years now, and it's just absolutely fantastic. The community is always wonderful. I'm like so grateful for all of you. If I have a question, the answers that I get are just so thorough and helpful. It's really fantastic. So that's been the most important by far. But I also will shout out their cloud computing, which is going to be hugely beneficial, especially as I get into working with larger data sets. And to that end, the data sets. We've got some really amazing people who have loaded in data sets to be kind of like ready to go. And I'll be checking those out to see if any of them will fit this need. And that could really accelerate my workflow. So excited about that. All of this will hopefully end with me contributing back a machine learning parameterization of air-sea fluxes, or even a reconstructed data set. So one of those flux products that's applied retroactively. So I will end there and move to any questions that you guys have.
Really nice talk. Are there like important observational uncertainties to consider with some of these measurements, like noise, or bias,
100%.
or representativeness errors?
Yes, 100%. So all of this work is assuming that we want our product to be closer to that observation, right? I'm assuming a certain like reliability there. As any of us who have ever been in the field know, that isn't always the case. You've got instrument errors, you've got uncertainties. And so there is a concern there. My hope is that by pre-training on bulk algorithms, you're bringing in a certain level of existing knowledge and accepted practice that then when you transfer on the observations, you're getting a more robust estimate. But yes, you're absolutely right. Observations are not 100% reliable. And I would love to also build in some uncertainty quantification to that end. I think it'd be really cool.
Thank you. It was great. Could you please get back to your workflow?
Sure. You know what? I'll just land on this version.
Do you think is it a fair comparison? Because training on the second part, comparison and at the best situation is going to learn that kind of models. So at the best scenario, it's going to be as bad as those models. So I suggest to have a third option that directly train on the observation to see what would be situation, what would be the effect of fine-tuning or transfer learning. So right now we skip this scenario here.
So I am pre-training on observations and then also fine-tuning on observations. That comparison is in there. You're right that it's not a totally fair comparison because these comparison neural networks that have only ever seen a bulk algorithm have never seen observations. The only reason I'm including them is because that's what flux products in this space currently do. They are currently just trained on the bulk parameterization, and then they're validated against observations that they've never seen. So that comparison NN is really just included to get at, and this is kind of where we're currently at in the space. And so as you can see, fine-tuning does get those products closer to observations. So if we take that as something that is desirable, we want to be closer to observations, that's a good thing.
I totally agree with you, but I'm really curious to see what is the effect of training on these bulk algorithms. If we want to figure out the effect of these algorithms, we need to know that if we exclude them, what would be the results? This is my point.
So to clarify, this is not an ensemble approach. So each of these is a separate neural network.
I understand. So you train on a synthesized data which generated by one of these models and then fine-tune on the observation.
My data is not coming from a model. My data is coming from observations.
So
for these bulk values, the inputs are always going to be the same. And then the flux values are calculated based on the bulk algorithm. For my covariance run, again, input's the same, but the flux value is coming from that actual physical measurement. And we can definitely discuss after.
Hi, thank you for the talk. I'm not sure if you mentioned this already, but when you were kind of training your neural network, did you pass in the whole data set, a subset of the data set, like a halo around your points, and how did you kind of like decide what method to kind of take with that?
Absolutely. So I experimented a little bit with doing batches. I landed on just passing the entire data set because the data set's currently still quite small. So I just thought that would be best for now. When I move into working with a global data set, I think I probably will use batches.
And we do have time for one or two more questions if there are any more in the room.
Hi, Julia. Thanks for the nice overview. So I'm not familiar with a few of the papers that you mentioned.
Sure.
So I hope it's okay if I ask questions about them.
Absolutely, but I will add the caveat that I'm no expert on those papers.
So I know the first one that you mentioned by Burasa, where they were trying to speed up.
Yes.
This is like 14, 15 years old now.
Yep.
Um,
And actually, this one was doing the same thing. It was trying to speed it up for inclusion in a NOAA product, and they were successful.
oh, okay. And what was the Chan paper, the next one doing?
Mhm.
Were they trying to speed up as well, or?
I think that they were trying to experiment with different machine learning methods to predict latent heat flux. Latent heat flux is it's not just my problem child, it's a problem child in air sea fluxes, as I'm sure you know. It's very difficult to estimate. Observations can be uncertain because it is related to the water cycle. So rainfall that affects measurements would obviously bias our latent heat flux calculations. So I think that this paper was just trying to look at, can machine learning give us an improved estimate? I don't think it was focused on speed or computational value. Because again, it wasn't pre-training on the bulk algorithms. It jumped right over that. It was just focusing on reanalysis data.
Okay, then maybe you can say a little bit more about the reanalysis data. So how is the reanalysis data different from bulk output?
I'm not sure. I would have to double check what they use.
And I also remember that at some point, I'm sorry to just keep wrapping.
No, you're so fine.
At some point, there was a talk here, I think a few months ago, where they said that, when Burasa did their study in 2007, computational speed was a problem.
Yeah.
But now things have gotten much faster.
Mhm.
So it's unclear if there's like a need to
So
speed these things up anymore.
I would then say that that's where this paper kind of comes in, because this was only in 2016, and actually this project has been updated even more recently than that. So it is something that they're still looking at. And even when I run the bulk algorithms on my computer, I notice a difference. Like even training my neural network is faster than running the bulk algorithm. So once it's trained, it's definitely faster. So I think that there is an advantage there. Obviously, if you're working with like a supercomputer, maybe the bulk algorithm is not your main concern for computational expensive operations. But yeah, it's something that they've been considering.
Just one final one. So for the transfer learning stuff, and maybe this is future work, like, do you have any plan to try and understand, what changed about the model when you did the transfer learning?
Yeah. So I've built into my code a lot of, so I showed, I'm trying to remember where it was, these approximations. So, assuming a fixed reference density versus otherwise, or effect, or including that adjustment for the 2% salinity in specific humidity. I'm building a lot of that into my code so I can kind of start turning these approximations on and off and figure out, this paper actually did a fantastic job of attributing, what is the effect of this approximation. And there's another paper, Tang et al. 2024, that does a really beautiful job comparing a lot of these products. And there are many papers that compare the bulk algorithms, as I showed, getting into like the precipitation slides. But nothing has done both. Nothing has ever really looked at like, okay, what's the effect of all of these simplifying assumptions, and also the difference between bulk algorithms, which vary in which assumptions of those they make. So I think building all of that into my code to kind of give me like an on-off switch for each one will really let me see like, okay, what's the improvement of the transfer learning, and what is improved just because I'm not making some of these simplifying assumptions, for example.
Thank you.
Thanks.
Thanks, Julia. Really great talk. I'm just wondering, so I'm not familiar with these bulk parameterizations at all. If you could go back to that slide where you showed like versus wind speed, the different predictions from different assumptions. No, maybe one more.
This one is showing, oh, that's not for wind speed.
Yeah, that's not the one I was looking.
That would be probably,
I think it was oh,
this
that
one.
Yeah. I'm wondering, like, in these bulk calculations, what inputs are going into calculating that coefficient? Like, do you think they just have the wrong inputs, that they're trying to force a single line when there really should be like a fat chunk as you show in the transfer learned one?
Maybe. I also think that that's a function of just like spread and measurements as well. And again, these are empirical fits, so they are fitting that line. Yeah, so these bulk algorithms, they all take those globally available predictors, you know, so it's really just like the temperature, the specific humidity, the sea level pressure. But they use those things to estimate other things in the interim. So, you know, they'll estimate what the roughness might be, and they're kind of this relationship is trying to account for that. So, you know, that's what it's getting at.
So these coefficients have the opportunity to have all the same inputs as your neural network, just the difference is
Oh
you
yeah,
have
oh
a
yeah.
more complex relationship that the inputs are all the same.
Right now, my neural network actually has one less input than this because I'm assuming a fixed sea level pressure. And some of these models don't do that. Some of them adjust them. So that actually would be a reason that they should be outperforming. And again, might be the best thing I could do to get my coefficients runs to improve to the level of my fluxes. Because these algorithms have those approximations built in, right? Like they know how to estimate the surface roughness and things based on those inputs, and that might be quite a lot to ask a neural network to learn. So.
Okay, I think those are all the questions. Thank you, Julia,
Thanks,
for kicking us
guys.
off.